Thanks to Margarita for inviting me here. Well, this is a sort of a visit, a virtual visit, but still, it's great to meet people virtually. Yeah, so like Leo just said, in my talk today, I'm going to be describing these new kind of optical transients known as fast blue optical transients or FBOTs. And I'm going to talk about the most extreme FBOTs, the ones, already FBOTs are something that are considered to be extreme versions of supernovae, but the class of objects that I'm going to talk about today will be extreme even for FBOTs. It's primarily based on the result that we published a couple of months ago, 2 months ago. And it's from this famous FBOT known as AT2018cow, where we identified these quasi pulses from the X-rays using the nicer telescope. And hopefully, it'll be clear what I mean by quasi and things like that as we go through the slides. But again, please stop me at any point if something is not clear. Like I said, I want this to be more like a discussion rather than just me talking straight for 45 minutes. Before I start, maybe I should just clarify why this object is called a cow. If you just read about this object, the first thing that comes out on Google is like a picture of a cow, and it's always referred to as the cow. And unfortunately, it has nothing to do with cows, believe it or not. The object is named AT2018cow because of pure chance. So the way it works in the time domain community is optical sky surveys that are operating from the ground. They scan the sky every night. They detect hundreds or even thousands of transients every night. Some fraction of them are followed up for further investigation, try to classify them. The ones that get classified, they're all given a name that start with AT. So A is for astronomical, T is for transient, and then the year in which they're discovered, 2018, this particular one. And then the first transient of 2018 will be AT2018 AAA. The second one will be AAB, and so on. And this particular one just coincidentally happens to be COW or cow. So you could guess just from this that it was 26 times 26 times 3, so roughly whatever that is, on the order of 2,000 transient that was classified in 2018. Okay, so now that is out of the way, this is the brief outline for what I'll be talking about today. First, I'm going to give really, really basic introduction to compact objects. I was told there'll be some students. So for the experts, this might be just too basic, but I'm just going to put it in there. I'm going to talk about what I mean by compact objects, where can we find them, and what are the conditions under which these compact objects form. And then I'm going to dive into this class of objects known as fast blue optical transients, or FBOTs, as I would call them. Some people call them FELTs, fast evolving luminous transients, and some people call them FOTs, fast optical transients. But in this talk, I'm just going to refer to them as FBOTs. And then I'm going to discuss the properties of this extreme FBOT, AT2018cow, and then some of the results and what they mean for the nature of what is powering these fast blue optical transients. So for the introduction, let's just dive in. And, imagine that you're an astronaut and you want to launch yourself off Earth, which is roughly 8,000 miles. Then in order to escape Earth, you'd have to launch yourself roughly at 25,000 miles per hour. That is the escape speed of planet Earth. Now, if you were to compress Earth by a factor of 10,000 by keeping the mass same, in order to escape Earth now, you would have to launch yourself at roughly 2.5 million miles per hour. So that's a huge increase in the amount of energy you have to give yourself to get out of Earth's gravity. Now you can take this to the next level. You can squeeze Earth all the way down to the size of, say, a blueberry, 1 centimeter wide, by keeping all the mass still intact in there. And now if you want to try to escape this blueberry-sized Earth, you will not be able to, because you would have to push yourself faster than the speed of light. So this blueberry-sized Earth will essentially collapse under gravity to form a singularity that is hidden away with the event horizon roughly the size of a blueberry. Luckily, Earth does not contain enough mass to collapse into a black hole. The sun, which is much more massive than the Earth, roughly 4,400 billion pounds, or multiply that by 2.2 kilos, still does not have enough mass to collapse into a black hole. In fact, a star that is much more massive than the sun, roughly 8 to 20 times heavier than the sun, that can collapse, but not all the way down to a black hole. It will be supported by neutron degeneracy pressure and form something called a neutron star. In order to form a black hole, you need something even more heavier. You need something like 20 solar mass star, more than 20 solar mass star. And that, at the end of its life, can collapse, and even the neutron degeneracy pressure will not be enough against gravity, and that will eventually collapse to form a black hole. And when these really massive stars collapse under gravity, they produce supernovae. Here is an example of a real supernova remnant. This particular one, I believe, is about 1,000 years old. But the takeaway point is that when the actual supernova happens, the explosion creates a lot of mess. There's a lot of mess around the newborn compact object that it's basically not possible to see through all that mess and identify the newborn compact object. However, if you have a supernova explosion that is highly asymmetric, then in principle, you can have a line of sight that is clear enough that you would be able to directly view the compact object that formed in the supernova. So just keep this in mind, that one way to identify that baby black hole / neutron star in supernovae is if you have asymmetric supernovae, like asymmetric explosions. And you have to be lucky in the sense that your line of sight has to be clear enough that it doesn't hit any of this mess that is produced. So here's just another animation of a typical core collapse supernova. We now know that the light curves that power the supernovae are driven by radioactive decay of nickel-56. This is just an animation. What's happening is the core of the star is collapsing, the shock wave is propagating outwards, it hits the surface of the star, and yeah, that is the explosion you see now. But the main point here is it produces light curves that sort of look like this. There's different classes of supernovae. I'm not going into the details of that, but just to give you an idea, the main takeaway point is these kind of supernovae, we know based on hundreds, perhaps even thousands of supernovae that have been detected over the last several decades, that they evolve on a time scale of few weeks. So the time from non-detection all the way to the peak might be a few weeks, and then it would be a few months by the time they go all the way down to non-detection. So they evolve, the ones that are powered by nickel-56 evolve on months time scale. So that brings us to this new class of objects called FBOTs, or fast blue optical transients. Like I said, traditionally, ground telescopes that scan the sky, they've been geared towards finding these long transients or long supernovae that evolve on weeks time scale. However, with the advancement in technology, both in hardware and also in software, these telescopes have been able to scan the same part of the sky multiple times in a given night. So you become more sensitive towards detecting things that change on a sub-night time scale. And that led to the discovery of this new class of objects known as FBOTs, or fast blue optical transients. So here is a sample that was collected by Maria Drought et al. In 2014 using the Pan-STARRS medium deep survey data. So what you're seeing here in each panel is a different object, And in each panel, you see multiple colors that correspond to different filters in which these objects were detected. And the gray shaded region here is type 1b supernova, a core collapse supernova. It's just for comparing, how these things are evolving. The main takeaway point from all these plots is that these fast blue optical transients are fast, meaning the rise time is on the order of a few days. So they go from non-detection all the way to the peak in just a matter of less than a week, and then they fade away in a couple of weeks. So typical time scale to have in mind is on the order of a month or two for these kind of fast blue optical transients. They appear in external galaxies, nearby galaxies mostly. And here's just the sample that Maria Drout compiled. And these are the images of the host galaxies. The takeaway point is that they're not coming from the very centers of their galaxies. They're offset from the centers of galaxies. So that's telling us these fast blue optical transients are not related to the supermassive black holes in the centers of these galaxies. So they're not a nuclear phenomenon. They're happening throughout the host galaxies. And it's not just pan-STARRS that has detected them. Here is another sample that was detected by the Dark Energy Survey. Again, the same trend. These are actually much faster than the ones before. You see the same trend, essentially, few days to the peak and then fade away in 2 or 3 weeks. Here's one really beautiful one detected by Kepler. So Kepler, for people who don't know, it was a planet finding mission. What Kepler did was just looked at one patch of sky for a very, very, very long time. And luckily, this particular fast blue optical transient happened to fall in that Kepler's field of view. And that enabled this unprecedented sampling of the light curve, the overall F-bar. So this is the host galaxy 2 months before the explosion. You see nothing there, but near the peak, you see this new object appear.
So, sorry, quick question. So do we know, like for this one, the redshift of all the others, the pan-STARRS, the DESI, like are they all this closer? A few hundred megaparsecs?
Yep. So the redshifts are known to the ones I showed before. It's they're all within a gigaparsec.
Okay.
Yep. Yeah. So you have to find them, soon enough so that you can follow them up. Yep. So this particular one was extreme in the sense that it increased by a factor of 300 in just 2.2 days, which is really fast even for an F-bar.
Sorry, a question. During the decay phase, there is like a change in the slope. Is that typical of the,
This one? Yeah. So in this particular case, they actually model it with interactions with the circumstellar medium.
Oh, I see.
Yeah, like really powerful shocks with dense medium.
And in the pan-STARRS events, did they see something similar or not?
Pan-STARRS events are nowhere close to that kind of cadence, right? So pan-STARRS has like what? 6 data points, 7 data points.
Much
same
more.
thing with dark energy. So this one, you can see it's basically once every 30 minutes, right? So that kind of unprecedented cadence is just, we've not seen this kind of cadence again since this one event.
Okay, thank you.
How long was the rise? Because it's really, really fast.
Yeah, it's 2.2 days.
Whoa.
Yeah. And I think they did all the things you do to make sure this is not some sort of a foreground star that is flaring, because stars flare all the time. So they rule out it's a star in our galaxy. It's very likely associated with this galaxy, which makes it F-bar luminous. So like I said, the main distinct feature of these F-bars is fast rise time. So on the x-axis here, I'm showing you rise time, which is defined as time it takes from half of peak to reach peak. And then y-axis is the peak luminosity. The stars mark the pan-STARRS discovered F-bars, and the circles and squares and these hexagons are other types of known supernovae. These are superluminous supernovae, these are core collapse supernovae, and then there's also type 1As, which are the detonation of white dwarfs. So as you can see, F-bots occupy a distinct part of this phase space diagram. This is going to be important in the coming slide. The first thing is it's telling us, just based on observations, that they don't follow the trend of other supernovae. So there are something perhaps is different going on with these kind of events. To understand that further, more physically, we can look at a plot like this, which is from this paper again, Maria Dowd's paper. And what you're seeing again is on the right side, on the bottom panel, we have the same thing, rise time. On the vertical axis, you have the peak luminosity. The same data points as before, well, some of them excluded, but core collapse supernovae, type 1A supernovae, and the F-bots. You can model, so basically you could use the underlying physics for these kind of systems that are driven by nickel 56, and then you can overplot the contours of how much nickel mass is ejected. So these contours, the solid lines, are the ones that correspond to different nickel masses that was ejected in the supernovae, and the dashed contours here, those represent the implied velocity of the ejecta. So as you can see here, for these regular supernovae, core collapse and thermonuclear, the amount of nickel that is generated is anywhere between 0.01 solar masses all the way up to 1 solar mass, right? These are the contours, the solid lines. And now if you look at the F-bots, you see a similar distribution. The amount of, if you want to apply the nickel model to F-bots, then the inference is that they have similar amounts of nickel produced in their explosions. However, the key is the implied outflow speeds of the ejecta. So for the same nickel mass, these things are much faster. So they are ejecting the ejecta are moving at a much faster rate compared to your core collapse supernovae, at least an order of magnitude faster. So that is the distinction to be made here. And also, if you pick a certain ejecta velocity, like for example, you pick 5,000 kilometers per second, then any data point to the top left of this curve will be physically will be unphysical, because those values correspond to mass of ejected mass of the ejecta being less than mass of the nickel 56, which is just not possible, right? Because nickel 56 is produced in the explosion, and you cannot have more nickel mass than the ejecta itself. So for a given velocity, these ones are all physical. If you assume 5,000 kilometers per second, then all these values just are not physical. If you assume extreme values of 0.1 C, which is over here, then these stars are not feasible. You still have these values. But the idea is, if you apply the nickel 56 model, then you really need to push things to an extremum. So the takeaway from the previous slide is that you require a substantial amount of nickel, sometimes unphysical, if you assume a certain ejecta speed. And two, in general, the required ejectas, the required shock speeds on the order of 10% of speed of light, which is very fast compared to your typical supernova. So given these sort of problems, people think there has to be some additional source of energy that is driving these explosions, that is driving these extreme luminosities in F-bots.
And quick question. So how many F-bots do we know of?
So now the sample is, I think, huge. We have hundreds, I believe.
Okay.
Over 100, I think, definitely, for sure.
Okay. but just one cow.
Our cow type are about 4.
Okay.
So this additional source of energy, in order to explain this additional source of energy, people have proposed different models. Some of them are listed here. One of the ideas is that you have a shock that is interacting with a very dense surrounding medium that can explain the excess energy. The other idea is you can form a rapidly spinning neutron star in a supernova. And because there's so much energy in the spin of this pulsar, you can radiate away some fraction of it and explain this additional energy that you're seeing. The third idea is you can have fallback accretion from the outer layers of the star that has collapsed onto the newborn compact object. And the other idea is maybe it has nothing to do with supernova, but perhaps it is an intermediate mass black hole disrupting a white dwarf, could produce a similar signal as FBOTs. And there are a bunch of more other ideas, but all of them can be put into three basic classes. Ones that involve shocks, ones that involve intermediate mass black holes, and ones that involve regular black holes / neutron stars, compact object, like 10 stellar mass black hole / neutron stars. Now, that brings us to AT2018cow. This particular object was the brightest FBOT. It still is the brightest FBOT, and also it is the nearest FBOT, coincidentally, and it's the most extreme in that sense. So here are some of the images of the host galaxy of AT2018cow. On the left side is 15 years before the cow happened. That is the green circle there. You don't see anything as expected. And here is near the peak of AT2018cow. You see this very bright blob that outshines the entire galaxy. And then roughly a month after, you see the overall emission dropping. So this particular galaxy is very close by, redshift of only 0.06, roughly 200 light years away. And really the thing that was really valuable to the community that allowed all these follow-up studies is because the people who discovered it, I believe it was the Atlas team, they discovered it right here at the peak. There was a non-detection 3 days before that. And that night, they put out an astronomy telegram. So for people who don't know, astronomy telegrams are little short notes that people in the time domain astronomy community share or sign up to. So anytime, let's say I discover some really cool transient, I could put up a little note saying, hey, we discovered something in this part of the sky, and people who are interested can follow it up. So that is what they did. They posted an ATEL that night saying, we discovered a very unusual optical transient that increased in magnitude by 5 within 3 days. So that gave a sign to everyone that this was not your typical everyday supernova. Something was dramatic about this. So everyone who was interested in transients followed it up, with whatever telescopes they had access to. There was a huge explosion of ATEL saying, hey, I looked at it in X-rays, hey, I looked at it in radio, millimeter, so people were really excited about this particular transient, which generated a lot of interest. And luckily, like I said, people also followed it up in the X-rays. So SWIFT is a telescope, small telescope, operated from the NASA Goddard Space Flight Center, and they saw X-rays from this particular event. Here is the light curve for the first 50 or so days. You can see a decline in the overall flux, but also, interestingly, there is variability on top of it on timescales of tens of hours. Now, when X-rays are present, that is really exciting, because when you see X-rays, that is telling us that whatever material is that is producing X-rays has to be very hot, millions of Kelvin. And I should say that NICER also looked at it, which I'm going to talk about in a little bit. So here's in red is the NICER data. The difference between NICER and SWIFT is NICER is 25 times bigger, so it collects way more photons than Swift. And NICER has extremely good timing resolution. It can precisely pin down the time of arrival to few hundred nanoseconds. So you can tell exactly when the photons from the source hit the detector. And hopefully it'll become clear in a couple of slides why that is important. So like I said, if something is emitting X-rays, then we know that material has to be hot, very hot, on the order of million or so Kelvin. And we know
fitting a black hole.
So we know that accreting systems emit X-rays, especially X-rays that change with time. So here's just an animation showing you have a black hole, some sort of an accretion flow around it. So some sort of an accretion flow around it. And what's happening is you have the material from the outer regions of the accretion flow spiraling inwards. It's losing gravitational potential energy. There is friction within the disk. Some of it is converted to heat. And when things get really close to the black hole, they get to millions of Kelvin, and that is when they emit X-rays. So by studying X-rays from accreting compact objects, we get to study the compact object itself. Because the X-rays are coming from a region that is dominated by the black hole's gravity.
Excuse me?
Yeah.
How was the spectrum in X-rays? So it's completely thermal, or is that possible that it's non-thermal?
Yeah, it was completely non-thermal. It had an index of 1. Yeah, non-thermal was the X-ray spectrum. It was highly non-thermal.
And what is the power law index?
I believe 1.7.
Okay, thank you.
Yeah. So some of these accreting systems are known to produce regular changes in brightness fluctuations in the X-rays. So here I'm showing you these signals that have been detected from black holes of all size scale and also neutron stars. In the top here are these stable signals that are produced from stellar mass black holes. In the middle are intermediate mass black hole candidates, and the very bottom panel are supermassive black holes. So the takeaway point is these are power density spectra of sample systems. And for stellar mass black holes and neutron stars, sometimes you see broad peaks in their power density spectra on the time scales of milliseconds, so hundreds of hertz. From intermediate mass black hole candidates, you have signals in the power density spectra again on the order of a fraction of a second. And then from supermassive black holes, you have minutes to hours time scale. And there have been some reports that you can have days as well, depending on how big the black hole mass is. So we already know this from decades of work that when you have a compact object that is accreting material, sometimes under certain conditions, it can modulate the X-rays and produce the signals. And depending on the time scale of these signals, you can make a statement about how big this compact object is. So now that brings us to our discovery. So the idea was, like I said, people were contemplating, oh, could this be a compact object power system where accretion could play some role in producing the X-rays? So I thought to myself, there's a straightforward way to check this. You essentially extract an average power density spectrum by combining the entire data you have and testing for signatures of QPOs or quasi-periodic oscillations in this system. And that is what I'm showing you here. This is the average power density spectrum that was acquired by NICER. And this is showing you how things are changing, the variability power on the y-axis as a function of frequency on the x-axis. Again, frequency, 1 over frequency is simply the time scale. So it's telling us how this object is behaving in terms of variability on time scales of a fraction of a second to milliseconds. The strongest peak in this power spectrum power density spectrum is around 225 hertz, which corresponds to roughly 4.5 milliseconds. So as an observer, the thing I care about most is the robustness of the signal, and that is what is being shown here. Where on the right side, I'm showing you the likelihood that this particular bump in the power density spectrum is from a noise fluctuation. So the point is, from this contour on the right side, the probability of seeing a signal as strong as the one seen in the real data in the noise data is on the order of 3.7 sigma, or 1 in 5,000. So that is what we assess based on the simulations that we performed. Ask me more about this, because the 20-page paper, 15 pages are about trying to assess whether the signal is real, whether it's some sort of a noise in the detector, or whether it could be a statistical fluke. So I'm happy to answer more about this if someone's interested in these aspects.
So is it the magic number 4 sigma? So this is slightly below.
I mean, I don't know what the magic number is. For some people, magic number is 6 sigma. But it depends what you call magic number. So
okay, I'm not a observer, but I recall that for other detectors, I don't know, there's one in Mexico called HEAP, and so for them to call a signal not a noise related signal, they normally use 4 sigma. So I don't know how this works here.
But also an important thing there is you have to account for the number of trials. So 4 sigma single trial, or is it 4 sigma, considering all the trials?
Yeah, all the trials.
Okay. Yeah. So yeah, I mean, it's up to you what you call is a magic number. It's a personal choice, I think. But like I said, this is not 5 sigma or 7 sigma result, but it's still curious, I think, enough to look for such things in the future objects as well.
Okay. Then what about the other possible signal that you have, like at 125 hertz, like that one?
It's not statistically significant, I think, because essentially all you have to do is compare against this simulation on the right. I don't think it comes out to be statistically significant.
Okay.
I think it falls below the 3 sigma line, which I guess is sort of magic number for me. So
okay, thanks.
So here is another way of looking at the same data, where in the top panel, I'm going to show you the power spectrum, the average power density spectrum. In the bottom panel, I'm showing you the amount of data that has been stacked. So what you will see is that the signal around 225 hertz should start appearing more and more stronger above the noise as I stack more and more data. That's what you should see. So the peak should be more well-defined as I stack more and more data. So yeah, so what I showed you before was the stack of everything. The movie was showing you, what happens if you increase the amount of data that you stack. The same way to realize that movie is this plot here on the right side, where on the y-axis, I'm showing you the SNR in those few bins of the signal, where we know the signal is from the average. And on the x-axis, sorry, on the y-axis is the signal to noise. On the x-axis is the amount of exposure that I have stacked. So as you see here, the SNR more or less monotonically goes up as I stack more and more data. And this is crucial. It's an important point, because what this is telling us is that this signal is stable throughout our 60-day monitoring program. So that translates to several billions of cycles. So now we can use this signal to make a statement about the models that have been proposed for the cow. Like I said, 3 different classes of models have been proposed The first one is one powered by a compact object, either a neutron star or 10 tilde 10 solar mass black hole. The second one is intense shocks that could hit the ambient medium and produce X-rays. The third one is an intermediate mass black hole. Shocks can be ruled straight up because we know shocks don't produce these kind of highly stable pulsations. So shocks are the first thing out based on the detection. At least for X-rays, you can't invoke shocks. And here's another really powerful argument we can use for making a statement about the upper limit on the mass of the object. So we now know that the X-rays are pulsing at a frequency of 225 hertz. So once every 4.4 milliseconds. Now imagine the X-rays are coming from some blob of a certain size, and that blob is essentially pulsing at 4.4 milliseconds, right, to produce the brightness fluctuations. Now, for this whole blob to pulse as one entity, all regions of this blob have to be causally connected. You cannot have one tiny part of this blob going up while the other part of the blob is going down. So everything has to be synchronously going up and down, meaning all parts of this blob have to be able to share information, so to speak, meaning information has to travel slower than obviously speed of light across the length of this object. And that is a very powerful argument, the causality argument. You take the speed of light, multiply by the time scale of your signal, and that gives you the absolute upper limit on the size of this X-ray emitting region from AT2018cow. And that comes out to be something like 1,000 kilometers. Now you can take this 1,000 kilometers number and you say, how much mass can it pack into this 1,000 kilometers before that mass collapses into a black hole? And that gives you an absolute upper limit on the mass of this X-ray emitting region. And that comes out to be something like 850 solar masses.
Sorry.
Yeah.
May I ask? So these numbers you are estimating, I guess they come from marginally bound and marginally stable orbits, right?
Nope. Actually, I do even more extreme. I say event horizon, all the way down to the event horizon. Maximally spinning.
Right. Right. But that depends on the spin, of course. The spin will make the marginally stable and marginally bound go to 1m rather than 2m. And they will go from 6 and 4m to 1m if you do that. But my question goes more in the direction of observing QPOs, and usually QPOs should come in pairs, like 2 to 3 or something like that. And usually those are, from what I remember reading, you have about, I forget the number, 60,000 billion cycles or something like that. And if you have that, that means it's a really stable signal for a very long time. So it's probably not a bright spot in the marginally bound or marginally stable or at the inner part of the disk, but rather somewhere where you have a warp in the disk, which would make it much more stable. So that's considerably further out. Are there any models using Kerr metric or something like that that would tell you what orbit, because that would bring the masses further down?
Yeah, that's a good point. Yeah. My next slide is exactly that. If you try to put this further out, then the upper limit on mass goes down significantly. It's the slide after. But just to answer your question, are there any models? I think there is a lot of debate on what is causing these quasi-periodic oscillations in neutron stars and also stellar mass black hole binaries, right? The 3 to 2 that you're talking about are specific kind of quasi-periodic oscillations from stellar mass black holes, the so-called high-frequency quasi-periodic oscillations. But you can also have low-frequency quasi-periodic oscillations, which could be from an inner disk that is precessing along your line of sight. So we don't know what kind of signal this is. The fact that it's stable is telling us that it has to be tied to something that does not change with intensity, which is mass and spin, right? This thing changed in luminosity by 4 orders of magnitude, and the signal is present, meaning it's not tied to the luminosity. Does that answer your question, or was I?
Yeah, I guess it does. Yes, from what you're observing, that indeed it's something very stable, and I guess the luminosity could change depending on the accretion rates, which would depend on the fallback and whatnot, or maybe if you have a magnetic field in there, you could also expect to have something modulating that as well. Yeah, in a sense, I was curious. So in order to have that many cycles, in there for a while, right? So it doesn't necessarily look like a magnetic field, but rather the geometry of space-time and the geometry of your disk, what's causing these sort of things. And of course, that would not be the marginally bound or marginally stable, but would be further out.
I mean, the marginally stable orbit or innermost stable circular orbit seems more like the candidate than much further out, right? Much further out, you can smooth out things as the accretion falls, but the marginally bound orbit always remains at the same radius, right? Independent of the luminosity. Independent of
Right. But if you had, well, I don't want to interrupt right now. So if you want, we can discuss this later on. But I think it's very interesting. Thank you.
So this upper limit is 850. If you assume the mass that you packed in has collapsed into a black hole that is spinning, maximally. So it's an extreme limit. So this 850 rules out also an intermediate mass black hole scenario eating a white dwarf, because you have a very stringent limit on the mass. So the only thing that remains are the ones where you have a compact object. So going back to this point again, what Enrique was saying, this 850 limit, I have assumed several extreme values. First, I've assumed that this blob of X-ray emitting region is sharing information at speed of light, which is obviously an extremum, because the way to think about this is, if you think about it as a Keplerian orbit, that is much slower than the speed of light. So that would bring down this mass further down. The second thing I assumed is that the information is actually being shared on entire 4.4 millisecond. It doesn't have to be that. And again, the rotation of the object matters. Like if I change the speed from maximally spinning to 0 spin, that instantly reduces this by a factor of 6. So in reality, this upper limit is likely a few orders of magnitude low, but I can't tell you, how many orders exactly. This is just a qualitative discussion on the upper limit is less than 850 for sure. Another really interesting piece of evidence that came from the cow is that people have taken radio observations, ALMA observations of the part of sky containing the cow. On the right side here is the ALMA CO map, molecular gas map. And the thing to note here is the star marks the position of the cow, and red means there's a lot of cold gas, molecular gas. Blue means there's no molecular gas, according to the size scale here. And what's really interesting here is that cow sits right next to a region that has a lot of cold gas. Cold gas means a site where stars can form. So that's one piece of evidence. And here are optical images of the field of view containing the cow, where star again is the cow. These contours are contours from this cold molecular gas. But the thing to notice here is this tiny dot that you see right next to the cow, to the bottom left of the cow, that is present in the blue filters, but not in the red filters. And these particular authors, they've actually modeled this little dot. And what they concluded is this is a young star cluster, meaning there's lots of young stars there. So the takeaway is cow sits in between. To the left in this image, you have this young star cluster. To the top right, you have this very cold gas region, meaning cow sits in a region where there's lots of ongoing star formation, star activity going on. So that is indicating that the cow is perhaps associated with some sort of a stellar explosion, rather than anything else, at least. So combining this with the signal that we detected, perhaps we caught a baby black hole in a supernova is the conclusion, or a neutron star. So one thing I did not say is that the signal that I showed you is called quasi-periodic because in the power spectrum, it's distributed over multiple frequency bins rather than one frequency bin. If it were perfectly periodic, then the entire signal would show up in one bin, but that's not what we're seeing. And that's why it's called quasi-periodic. It doesn't necessarily mean that it is not a pulsar, because we don't know, how this, if it were a pulsar, and if this spin is a representation of the pulsar spin, then it is possible that the pulse period was changing during the 60 days, and that could have manifested in some sort of a broadening of the signal in the power spectrum. So the point is, this 225 hertz could be in the ballpark of the newborn pulsar. So the obvious question then is, how many can we detect? How many such signals can we detect with our current telescopes? And the answer to that is based on the rates of these cow-like events. So someone asked me how many cow-like events are known so far. It's on the order of 4. 3 of them, I believe, have X-ray detections, but they're much further out. So we could do these kind of timing analysis on them. But the rates are something like 0.1% of core collapse supernovae. If you take that rate, then you can estimate, how many of them are present within the local volume, say a few hundred megaparsecs, because that is what you need for NICER, for example, to do this kind of timing analysis. So in order to directly detect these kind of quasi periods, you need it to be within a few hundred megaparsecs, and that happens once every 3 years. So it's low numbers right now. However, going forward, there is ESA's Athena telescope, which is going to be launched in the 2030s. That is going to be 10 times bigger than NICER. And when you get to 10 times bigger, you get to go much further out in space. And that will detect a few per year. So that is pretty much my presentation, but I'll just leave you with this little press release video that we made that makes it clear what the discovery is and what it means.
Scientists have theorized that when a massive star's core collapses, it will lead to the birth of a new compact object, either a neutron star or a black hole. However, there has been a scarcity of direct evidence for the creation of such an object. But a team of astronomers led by Dr. Dheeraj Pasham at MIT have uncovered new evidence from AT2018cow, an explosion that happened 200 million light years away. It was 100 times brighter than a typical stellar core collapse and sent forth bright X-ray emissions. Using the NICER telescope, astronomers discovered a highly stable pulsation in X-ray brightness with a period around 4.4 milliseconds. Combining this timescale with the fact that information cannot travel faster than the speed of light, they concluded that there has to be a compact object at the heart of AT2018cow. These findings suggest that we might be witnessing a newborn compact object interacting with its environment in a manner never seen before.
We actually produced a video in Spanish, but I thought I included the Spanish version, but sorry. So yeah, thank you.
Don't worry. Thank you.
Okay, let's start with a session of questions. If you have, please raise your hand. So Fabio, please.
Yeah, I have a question. So how long does this quasi-periodic oscillation last? From
So
the emission to the end, or during a certain period, or how is that?
So this particular power density spectrum that I showed you was using the entire data, like all the data that we had with NICER. I extracted the time series power spectrum and just stacked them on top of each other. As you can see, it's not really possible to like divide the data into chunks. We did divide the data into chunks, and it's present at a lower significance, obviously, early part and also at late times.
Yeah, so during several weeks, right?
Yep. But these things only last for a few weeks.
And if the X-ray emission comes from the region around the black hole or neutron star, what is the maximum density of the medium that you can have around in such a way that the X-ray is not absorbed by the medium? The X-ray needs to cross the region between us and the region where it is emitted, no?
Yeah, so we
can it be there?
Yeah, I mean, we can directly fit the X-ray spectrum and estimate the line of sight column density, right?
Okay. Yeah.
And I don't remember the values off the top of my head, but those values, like, yeah, they exist. It's pretty straightforward.
They are in your paper.
It's there in Rafaela's paper, but yeah, it's there.
I see. Thank you.
Yeah, we can actually track the NH as a function of time too with the NICER spectrum that we had.
Okay, thank you.
Okay, Margarita, please.
Yeah, I have a kind of observational question, because you said that we are waiting for Athena to be ready, but how about Chandra and XMM? Why they don't they are not useful for that? Because they is not monitoring, or why? What are the limitations of those instruments?
Yeah, good question. We cannot use Chandra, Swift, or XMM because the signal has, as you can see, the time scale is 220, or frequency is 225 hertz. And Chandra, you cannot sample at such a high rate. Well, you can, but it doesn't make, the count rates are going to be just too low. You're not going to be able to do anything. With XMM, there's a timing mode that you can use, but that is very poorly calibrated. I've never seen anyone report like hundreds of hertz signal from any system with XMM. So the simple answer is timing accuracy with NICER is far more superior than any other telescope.
The other question is similar to what Fabio was asking, but how long would you expect this signal to survive? And you said that this transient lasts a few weeks, but I'm not sure if you were referring to the optical emission or the X-ray. I mean, this PPOs, because you were showing how this signal was stronger as you add up the observations. I mean, if you observe now in a very late epoch, can you expect to see something in the X-rays if it was a pulsar or something?
Yeah, so it was not detected in X-rays after day 50, as you can see here. It's just not detectable right now. There's nothing to detect in X-rays. It's faded in X-rays, optical. It's gone.
Normal, but if you, I mean, I don't know if it's my ignorance maybe, but if you have the signal in the compact object, why does it disappear? And yeah, what?
Well,
it was not intrinsically on the compact object, maybe in the disk.
I mean, if you imagine it's a neutron star, and let's say this signal is a hot spot, a bright spot on the neutron star that is going around along with the spin of the neutron star, then there is no bright spot that is producing this. After a certain time, temperatures change, maybe the bright spot disappeared and the overall flux went down. There's nothing accreting onto the neutron star, right? So if there's no accretion, there's no X-ray emission, there's no hotspot, hence no signal. Does that make sense?
Yeah. Okay, thank you.
Yeah, we made you. Yeah.
Okay, Yuri, please.
Yeah, hi. So basically, the swift light curve you're showing here is the Rivera-Sandoval et al. Light curve, I guess.
Which one?
The swift light curve is the Rivera-Sandoval 2018 light curve, right?
I mean, this is something I just reduced. Yeah, but it's basically the same as what she got. Yeah.
Okay. And the other question is your QPO signal. You say is present everywhere, right? Does it become stronger or weaker during the flares?
I don't think we have that kind of data to do time resolved power spectra. There's no way. So you're asking if I can like take a power spectrum here, like there?
Sort of, yes.
I don't. There's no way we can like tell. You're not going to be able to detect anything if you just take the tiny snapshots. So this is a signal that you have by integrating like the entire data. If you only take
because you made a movie, right? Oh, yeah. But okay, I see. So when you did the movie, you just kept increasingly stacking data. You didn't do.
No, I'm just stacking one at a time.
Oh, I see. Okay, all right. Okay, thanks.
Okay, let's continue with Enrique.
Yes, thank you. One of the intriguing things here is you're trying to find what the source is. And if you were to consider something like a weird kind of supernova that lasts very little, you would expect the view of the compact object to be opaque, right? You wouldn't expect to see something there, because you have all this material that came out from the explosion. If you had something like a GRB, then probably a jet could clear the way, but I'm not sure that there is any clear evidence in GRBs where you actually can see QPOs from the central engine at work at some point. I don't think there is. So the places where I can remember that you see QPOs are mostly micro quasars or something like that. I mean, on this order of very short periodicity. So in that sense, isn't that telling us very strongly that we should be probably close to the region where a jet could come out, so that that cleared whatever material was in that direction, if there was a jet, of course. And if there was no jet, then that all the accretion is occurring equatorially, or in the plane of the, if there's a binary, for example, in that plane, or I don't know. I'm really surprised that you can actually see QPOs in such a bright object. I mean, this is competing with superluminous supernovae, right? So it's very, very bright. You can see QPOs from that. So that could eliminate a whole bunch of possibilities and tell you, hey, we're observing a central engine right there. I don't know if that has been done in any other in any other transient.
Yeah, so the answer is no, it has not been. So that's why it's exciting, because you're seeing the central engine directly, right? So Rafaela wrote a paper about this, a couple of years ago, the first initial initial data. And what she suggested, independent of this, is that the fact that you're seeing X-rays already without this pulsation is telling us that the explosion must have been asymmetric. somehow you're getting a clear line of sight to the central region, right?
But X-rays could come from elsewhere. It could come from a shockwave or something. The fact that you see QPOs changes completely that picture.
Yep. So that, yeah. So I think so too. So exactly. So you can have very dense medium and that can shock and heat up temperatures and produce X-rays. Yes, the shocks can also produce X-rays. And you have very lumpy surrounding medium, then you can have variability on, you know, days or tens of hours time scale. But like you said, the time scale is key here. The time scale that is so short, I think, is a sort of nail in the coffin argument that there is a compact object. No other way, I think.
And just to something that would probably, so there's a couple of things with the data. 3.7 is probably not too high, but it's also not too low. So yes. The other thing there would be, how sure are you that they are coming from the same? So what's the spatial resolution of, I guess, NICER to make sure that both the F-bot and the signal are coming from the same object? And what would be the chance that it's a coincidence, a separate event but in a nearby location, of course, close to a star-forming region?
Yeah, so great question. But yeah, like I said, most of the paper is about, can you see this here? Yeah, so this on the right side is an imaging telescope taken with XMM when cow was active. That is cow.
I can only see your background, so I'm not sure.
Sorry.
Yep.
Yes.
I thought I shared. Oh, can you see it now?
Yes, thank you.
Sorry about that. So yeah, so I'm showing you two images of the same part of the sky. On the right side is the image where the cow was active and bright. On the left side is long after the cow disappeared, after day 60. And the red circle is the field of view of NICER. And as you can see here, you know, the cow was pretty much the only object in there. There are these other fuzzy things, but they are way off axis and they cannot produce this kind of signal. And then, yeah, there's several tests in the paper. Like I said, majority of the paper is trying to assess, because it's, yeah, I think we think it's an extraordinary result. So extraordinary results need extraordinary proof. So we think we did everything in our, you know, whatever we could do to assess the significance or robustness of this. Red noise is one thing that is absolutely critical to characterize, that can produce these kind of signals. And that is something that we spend a huge amount of time on. You know, if you're interested, you can go look at the things that we did to make sure this is not due to red noise. You know, NICER is made up of several detectors, several backgrounds can come in. So we looked at all the different kinds of backgrounds to make sure this kind of signal doesn't pop up. That's what is shown in these 4 different backgrounds. And NICER is made up of actually 8 or 7 units. And you know, similar signal is seen in all units, which is telling us that it's not something local to the, and it's actually astrophysical. So yeah, there are several things that we talk about in the paper. And we don't think it's related to the noise, detector noise.
Okay. All right. Okay. Very interesting result. Thank you.
Thanks.
Okay, Yuri, do you have more questions?
No, sorry, I left the hand.
Okay, so let's continue with Pablo.
Yeah, just 2 comments. So one is that there were observations of QPOs in jets associated to TDs, right? There was a paper by Reis.
Yeah, Ruben.
That's mainly for Enrique. The other one is about X-ray emission. So again, in the case of GRBs, you basically can't see QPOs because the afterglow is so bright that that covers any emission from the central engine. No? So here again, if you have a relativistic jet crashing against a dense medium, that would produce a huge amount of X-ray emission too. No? So I'm wondering if people have estimated limits from that. So if the X-ray emission comes from the central engine, it means that the afterglow emission from a possible relativistic jet should be very small. And if the relativistic jet is pushing against a shell or something like that, I don't know, that will produce a large X-ray emission.
That's correct. It can produce, in fact, the X-ray luminosity that is given, that is coming out of this one, can be fit with extreme versions of what you just said. There are papers by Ori Fox who claims, that was before the QPO thing came out, that you can explain the X-ray emission through interactions with the ambient medium. But like I said, I think the presence of QPO rules that out.
Yeah. So the point is why the jet is not emitting X-rays, or why the X-ray emission from the jet is smaller than the X-ray emission from the central engine.
I mean,
it's something that probably needs to be investigated, no?
Yeah, I think, yeah, I don't know off the top of my head. Why is this could be, who knows what it is. And that's why it's interesting.
Because it can't be absorbed because the jet is moving in the same direction from where the X-ray emission from the central engine is coming, you know? So if the X-ray emission from the central engine is not absorbed, neither is absorbed after the emission.
I agree.
Yeah.